Okay, so in this video, we are given a curve in the complex plane, which is gamma of t here, and we're given also this function f, and our goal is to find the integral of 1 over z dz over the composition of f and gamma. So to find this, we should first of all think a little bit about what gamma represents. So gamma is basically just this curve right here. So it's just the unit circle. And so f dot gamma is going to be the image of this curve under the function f. Now, I don't know exactly what the image of that curve is going to be, but I claim that we can use something called the winding number to figure out what this integral is going to be. So what does this mean? So the winding number of a function f along a curve, in this case gamma, is the number of times that that function f traverses the origin. So as an example, if f of z was equal to the identity, so if f of z was just z, then the image of this curve would just be the same curve. And when I traverse this curve, the total number of times that I wind around the origin is 1. So the winding number would be 1 in this case. Versus, right, so if this was maybe z to the 1/2 or square root of z, if we chose a certain branch for that, the image of the curve might look something like this. And in this case, the winding number would be 1/2. So it's the total number of times that it goes around the origin, or you can also think of it as the change in argument of the function, where if the change in argument is 2 pi, you would say that the winding number is 1, and if it's 4 pi, you would say that it's 2, and then so on. So that's the idea. So how can we apply this? Well, basically, this function 1 over z dz, if we integrate it along a curve, assuming the curve isn't like super pathological, so this integral is actually equal to 2 pi I, and then times whatever the winding number of the curve is, call that w. This is the integral of 1 over z dz. So if we can find this winding number, then we'll get the integral of 1 over z. So now looking at this function, what we can see about this function is that there are a certain number of zeros, and there's a fact about the winding number. There's a fact about this winding number, which is that this is always equal to the number of zeros minus the number of poles. Okay, so in the case of this curve, you want to look at the interior of this curve, and you want to look at this function f and look at how many zeros does it have minus how many poles. Whatever that is will give you the winding number of, in this case, f dot gamma. And so that's what we're going to use. But okay, so looking at this, so I have e to the z minus 1. And if you're familiar with e to the z, you know that this is 1 plus z squared over 2 factorial plus dot dot dot. If we take away 1 from this, so we're just going to have the z plus the z squared over 2 factorial and so on, I claim that this is actually equal to z. So the z is 0 when z equals 0, and then times this remaining part. So when I claim that this remaining part on the inside is not going to be 0, when z is equal to 0. So this function e to the z minus 1 has a 0 when z is equal to 0. And looking at this, we can see that it should be a 0 of order 1. Because when I have z is equal to 0, this part on the outside is 0, but this part on the inside is not. So this is a 0 of order 1. And if I multiply this by z, right, so f of z was z times this e to the z minus 1. And so that's just going to increase the power here. So I'm going to get a z squared here. So it seems like what I get is going to be a 0 of order 2. So I think what's going on is that this expression z minus p, if you count the zeros with multiplicity and use that to be your big Z, this should be equal to 2 in this case. So I think my answer is that this integral is equal to 2 pi I times 2, because I have the winding number is equal to z minus p. We figured out that there's a 0 of order 2, which is giving me that this is 2. And so this is actually just equal to 4 pi I. And that's it.